Good morning, viewers. I'm Teacher Betty, continuing with the mole concept. Today we are going to discuss heat or enthalpy changes. For many chemical changes or for many chemical reactions, usually heat is absorbed or involved. For the type of reaction where heat is absorbed, that type of reaction is called an endothermic reaction. The sign for heat changes is given as delta H. The sign for endothermic reaction is positive. And positive means heat is absorbed. For an exothermic reaction, heat is involved. So the sign for an exothermic reaction is negative. It is written as delta H, and the value is always negative. Uses of an exothermic reaction. An example I can give is burning of charcoal. Charcoal is carbon. Charcoal can be used as a fuel. Also burning of petrol in a car engine, that one can be used to provide energy. There are many heat changes involved in a chemical reaction. We can have heat of reaction, enthalpy of combustion, heat of neutralization. We can have hydration energy, dissociation energy, but at your level, we can end at heat of reaction, heat of combustion, and heat of neutralization. What is heat of reaction? It's the heat change when 1 mole of a product is formed from the reactants or from its reactants. And heat of combustion is the heat change. Heat of combustion is the heat change which takes place when 1 mole of a substance is completely burnt in oxygen. And enthalpy of neutralization is the heat change when 1 mole of hydroxide ion, which is provided by an alkali or from an alkali, reacts completely with 1 mole of hydrogen ion, which is provided from an acid, to form or to produce 1 mole of water. We can now see or study how we can determine the enthalpy of combustion. An example is ethanol. We can determine the enthalpy of combustion of ethanol. The setup of apparatus is drawn like this. You must have a metal can, a spirit lamp, a wick, and then ethanol of a known volume. Power ethanol of a known volume into a spirit lamp. Fix a wick and note the mass of the lamp together with its content. Then we are noting the mass M naught of the lamp together with its content. Then pour water into a thin metal can and note the initial temperature. The initial temperature, we can call it theta 1 of the water. After that, you light the wick and allow the experiment to stand for 10 minutes. It can stand for more time or for 10 minutes, whichever time you want. Stop the wick and note the final temperature. The final temperature, theta 2 of the water. Then you have to weigh the lamp again together with its content. And note the mass M1 of the lamp. You are going now to calculate the enthalpy of combustion of ethanol from mass of water, which is MW, can be obtained from density is equal to mass over volume. So mass of water is the same as density of water times the volume. The density of water is always 1 gram per cc, and the volume of water used, we use the 500 cubic centimeter. So the mass of water used will be 500 grams. Having obtained the mass, we can now go and get the mass of ethanol used to raise these temperatures. Mass of ethanol used up during burning. We can give it a constant as Me is equal to mass of the spirit lamp before burning, which was M naught, minus the mass after burning, the one we noted after burning. So we can get the temperature changes. Temperature change can be given delta theta is equal to the final temperature minus the initial temperature. So quantity of heat provided by ethanol to raise those temperature is given by quantity of heat bracket delta H is given by mass of water times the specific heat capacity times change in temperature. We have determined our mass of water as 500, so delta H is equal to 500. The specific heat capacity of water is always given to you, which is 4.2, and then the temperature change, we got it as theta 2 minus theta 1, which is equal to 2,100 theta 2 minus theta 1 joules. So that is the quantity of heat produced by ethanol to raise the temperature of water from theta 1 to theta 2. This heat was produced by ME grams of ethanol. So ME grams of ethanol produced 100 theta 2 minus theta 1 joules of heat. What about the relative molecular mass of ethanol, which is 46 grams of ethanol? Will produce, we cross multiply 2100 theta 2 minus theta 1 times 46 over ME in bracket joules, which is equal to 96,600 theta 2 minus theta 1 over ME joules per mole. Why do we say per mole? Because a mole of any substance is numerically equal to the relative molecular mass. Let us now look at a few examples. The first example is obtained from 2014, paper 1, number 30. Carbon monoxide burns in air to produce carbon dioxide according to the following equations. 2 moles of carbon monoxide plus oxygen to produce 2 moles of carbon dioxide. And the heat change is negative 572 kilojoules. Which one of the following is the molar heat of combustion of carbon monoxide? So when you look at our heat, negative, I told you, means an enthalpy change which is exothermic. So burning carbon monoxide in air produces an exothermic reaction. Now we are going to relate moles equations and heat of reaction. When you look at our equation, we are told that 2 moles of carbon monoxide produces this heat. From the equation, we have 2 moles. 2 moles of carbon monoxide produces how much heat? produces negative 572 kilojoules. What about 1 mole of carbon monoxide? Will produce, we cross multiply 1 times negative 572 kg over the 2 moles. So this is the same as 286 kilojoule per mole. So every mole of carbon monoxide will produce this type of heat, and our answer is C. Example 2 is obtained from 2015, paper 1, number 14. Which one of the following volumes of butane will produce 1,500 kilojoules of heat at STP on combustion? We are told that 1 mole of a gas occupies 22.4 cubic decimeters at STP, and the molar heat of combustion of butane is 2,880 kilojoule per mole. So in the previous lesson of standard temperature and pressure, we said 22.4 cubic decimeters at STP is the molar volume. So which means 1 mole of butane contains or occupies 22.4 cubic decimeter. And we are told that when each mole of butane is combusted, it produces this heat. So since this heat is produced per mole, so this heat of butane contains or occupies 22.4 cubic decimeters. Therefore, 2,880 kilojoules of heat is produced by 22.4 cubic decimeters of butane. What about 1,500 kilojoules of heat will be produced by, we close multiply 1,500 times 22.4 cubic decimeter over 2,880 cubic decimeters. And our answer is A.
Muli kuki tuli mu basi mulagawa tawuni kyanaku kikabya okabya kivo kya digito muzekwa nalogo. Eno basi tekyalina mataala, eno basi tekyalina mipiira, eno basi indiketa za ndali. Mugive mangu temufiiramu, ne gye mulaga teriyo mulamwa, kujjako okugwa mu binnya n'okufiira mu njaga. Mubeesige yasigaza bigambo, mayimayi azunga buzungu. Muli kuki tuli mu basi mulagawa tawuni kyanaku kikabya okabya kivo kya digito muzekwa nalogo. Mwasomako twasoma luzungu, kati mukolawa tuli ku street. Mulya biki? Tulya mandazi. Musulirira ki? Tusulirira pani kyanaku. Muli kuki tuli mu basi mulagawa tawuni kyanaku kikabya bukabya kivo kya digito muze kwa nalogo kituuka katako tuteekwa buteekwa kituuka katako tusaana kukyusa twenda pulezidenti mulala twagala musomesa twagala dokita bosa science atuwe vaccine atuwe treatment atuwe solution akitegedde tegeeza omulala atategedde tokoppa bukoppi kyannaku muli kuki tuli mu baasi mulagawa tawuni kyannaku kikabya bukabya kivo kya digito muze kwa nalogo
Example 3 is also obtained from 2015, paper 1, number 30. This one is going to relate the enthalpy change with mass. Alcohol burns in air according to the following equation. When we burn alcohol in air, we get carbon dioxide and water. The heat given out is 22,017 kilojoules per mole. Again, it is negative, meaning it is an exothermic reaction. Which one of the following is the mass of an alcohol required to produce 200 kilojoules of heat? So now we are told that each mole of the alcohol produces 2017 kilojoules. So from the equation, (217 kilojoules of heat is produced by 1 mole of the alcohol. Since they want mass, we go direct to the molecular mass of the alcohol. RFM of the alcohol, which is propanol. So this is the same as 3 atoms of hydrogen plus 7 atoms of hydrogen plus 1 atom of oxygen plus 1 atom of hydrogen. Carbon is 12. 12 times 3 plus 1 times 7 plus 1 times 16 plus 1 times 1. And the answer is 60. So having obtained the molecular mass of the alcohol, we go back to the equation. We are told each mole produces 2017 kg. So 2017 kilojoules of heat was produced by, from the equation, 1 mole. But each mole is 60 grams. What about 200 kilojoules of heat will be produced by, we cross multiply 60 times 200 over 2017. And our answer is, when you look at the answers, we don't have the answer that is similar to this. But the trick is, they have multiplied the denominator, both sides, by 2. If we multiply by 2 and by 2, the answer will be 2 times 60 times 200 over 4,034. And our answer is S. The example is obtained from 2004, paper 2, number 11, part C. In an experiment to determine the enthalpy of combustion of propanol, 0.54 grams of propanol was burnt, and the heat involved caused the temperature of 150 cubic centimeters of water to rise by 21.5 degrees Celsius. We are told that the molar mass of propanol is equal to 60. The density of water is equal to 1 gram per cubic centimeters, and the specific capacity of water is equal to 4.2 joule per gram per Kelvin. Calculate the experimental value of the enthalpy of combustion of propanol. So here we are going to first get the quantity of heat produced that raised the temperature of water to 21 degrees Celsius. So quantity of heat produced the letter H is equal to mass of water times specific capacity times change in temperature. So we can get the mass of water from density times volume. And this is the same as 1 times 150. And the answer is 150 grams. So good enough, we are given the temperature rise. So we can now go and substitute into this formula. Therefore, quantity of heat is equal to mass of water, which is 150 grams, times specific capacity, which is 4.2, times temperature change, which is 21.5. And the answer will be 13,545 joules of heat. So this is the quantity of heat that was produced by propanol to raise the temperature of water to 21.5 degrees Celsius. So this quantity of heat was produced by how much? By 0.54 grams of propanol. Therefore, 0.54 grams of propanol produced 13,545 joules of heat. What about the mass, the molar mass of propanol? 60 grams of propanol produced, we cross multiply 13,545 times 60 over 0.54, which is equal to 150,500 joules per mole. 2012, paper 1, number 38. Hydrochloric acid reacts with the sodium hydroxide according to the equation. We are told 1 mole of hydrochloric acid reacting with 1 mole of sodium hydroxide to produce a solid and water. When 25 cubic centimeters of 0.5 molar hydrochloric acid was added to 25 cubic centimeters of 0.5 molar sodium hydroxide, the temperature of the mixture rose from 25 degrees Celsius to 28.4 degrees Celsius. The molar heat of neutralization is, we are told that assuming the density of the solution is equal to 1 gram per cubic centimeter and the specific capacity of the solution is equal to 4.2 joule per gram per mole per degree Celsius. The answers are given to us as A is equal to 714 joules per mole, B 1,428 joules per mole, C 28,600 joules per mole, and D 57,120 joules per mole. So when we look at our neutralization reaction, hydrochloric acid reacting with the sodium hydroxide to produce sodium fluoride and water. If I write the ionic equation, I close those that are similar on both sides. So I remain with my hydrogen ions plus hydroxyl ions to give us water. Remember the definition of enthalpy of neutralization. When 1 mole of hydrogen ion reacts with 1 mole of hydroxyl ions to produce 1 mole of water. So this is a neutralization reaction. And we are told this was 25 cubic centimeters reacting with also 25 cubic centimeter. So the total volume of the solution is 50 cubic centimeters. Before we get the molar heat of neutralization, we have to get the quantity of heat produced. So quantity of heat produced the letter H is equal to mass of water times specific capacity times change in temperature, or mass of the solution times specific capacity of the solution times change in temperature. Are we given the mass of the solution? No, but we are given the density. So mass of the solution will be equal to density times volume. The density is 1 gram and the volume we have gotten it as 50. So mass of solution will be 50 grams. We are given the specific capacity of the solution. We can now get the temperature change. Temperature change is equal to the final temperature, which is 28.4 minus the initial temperature, degrees Celsius. And the answer is 3.4. The answer is 3.4 degrees Celsius. So substituting into this equation, the quantity of heat will be mass of water, which is 50, times specific capacity, which is given to us, times the temperature change, which is equal to 714 joules. So this is the quantity of heat produced. Let us find how many moles produced this heat. So we are told 25 cubic centimeter of 0.5 molar hydrochloric acid. We can either use the acid or the base. We shall get the same moles since the reacting ratio is 1 to 1. Moles of HCl. Capital M, I told you, means molarity, and molarity is the number of moles in 1,000 cubic centimeters. So 1,000 cubic centimeter of hydrochloric acid contains 0.5 moles. What about 25 cubic centimeter of hydrochloric acid? Will contain, we cross multiply 0.5 times 25 over 1,000 moles is equal to 0.0125 moles. So these are the moles of the acid that produced this heat. Therefore, 0.05125 moles of the acid produced 714 joules of heat. What about 1 mole of the acid will produce? We cross multiply 714 times 1 over 0.0125, which is equal to 57,120 joule per mole.